This is FOA Lecture number 64 in our series of lectures on fiber optics. This is an update of lecture number 25 on fiber to the home. We're doing this particular lecture on passive optical networks, which have become the prime way of building fiber to the home networks. So we'll talk about how they are implemented in a fiber to the home structure and what other applications they might have. A passive optical network is called that because it's passive. There's basically no active components between the head end or central office and the subscriber. Instead of using electronic switches, it uses an optical splitter that can split a single signal and broadcast it out to a large number of users. Passive optical networks were developed for fiber to the home, but they're also used in local area networks. It's a really low-cost, simple network that is easy to scale from small numbers of users to very large numbers, like everybody in a city. Because passive optical networks have been designed for large numbers of users, they have been also designed to be easy to manage. So adding or subtracting users or moving them around is much simpler than a typical network. Passive optical networks have some significant advantages over typical all-electronic networks. Because there are no electronics in the link, there are no places needed to site the electronics, provide power to them, uninterruptible power, perhaps heating and air conditioning. This leads to significantly lower cost, both capital expenditure, CapEx, and operating expenditure, OpEx. Passive optical networks can handle any kind of traffic. They weren't just designed for data, they were designed for triple play, voice, data, and video. Passive optical networks are also inherently secure because the splitter in the network sends the same signal to all of the subscribers. There is a privacy issue, and that's handled by encrypting in signals for each user. So each user is secure. This is a part of the network that has been particularly attractive to government and military users. The only potential disadvantage of a PON is the difficulty of figuring out where to put splitters in the network to maximize the connectivity and minimize the use of fiber. In the central office, or the head end, of a passive optical network is an OLT, an optical line terminal, which goes out on fiber to the splitter and then connects up to an optical network terminal, ONT, at the subscriber. Here's a typical OLT, optical line terminal. The equipment on the right is the OLT itself, with ports for outputs to splitters. Next to that is a fiber patch panel in the middle, and in the background is a router which connects up the internet feed for the network. This small network right here is actually enough to cover about 5,000 to 10,000 users. That's the advantage of having a single port in an OLT handle so many users. Not shown in the bottom part of the picture here is, of course, the uninterruptible power supply for it to ensure that if there is a power failure, the network keeps operating. At the subscriber end, there's an optical network terminal. That optical network terminal has the optics to go bidirectional on a single fiber. That's the other big advantage of a passive optical network. It operates on one fiber instead of two, like traditional full duplex fiber optic links. There is a receiver that receives signals at 1490 nanometers from the OLT, and a transmitter which transmits upstream at 1310 nanometers. Beyond that, there are protocol converters that go from a PON type, typically GPON, to Ethernet, to video for TV, and to plain old telephone service for the triple play service that is expected from a PON network. BPON was the first PON network to get widespread usage. Broadband PON was based on telephone company protocols. GPON, or gigabit PON, followed on based on more Ethernet type protocols and has become the most popular type. It's in use at probably 95 to 99% of all networks. EPON is an Ethernet PON which comes out of the IEEE and is based on pure Ethernet protocols, but is not as widely accepted as the GPON networks. The original PON System Specifications, which I apologize for being so small and hard to read here, but you can get them off the web pages on the FOA online guide. The original PON System Specifications basically were for a gigabit network and uses wavelength division multiplexing, 1490 nanometers downstream and 1310 nanometers upstream, to split for 32 or 64 users typically. BPON, which is pretty much obsolete, could go 20 kilometers. GPON has several different versions that go 10, 20, 40, or even 60 kilometers and can split for up to 64 different users. Since the original introduction of GPON a decade ago, engineers have been very busy developing, of course, the next generation. And that next generation of GPON is 10 gig GPON. There are 3 different versions. The differences are somewhat subtle, but basically they're designed to go longer distances at very much higher speeds and with more splits to cover more users. The easier to read version of this detailed table is on the FOA website in the FOA guide in a page called FTTH PONs. But basically the 10 gig PONs has a couple of very, very important differences. First, obviously, it runs at 10 gig. Secondly, it can go 60 kilometers. Thirdly, it can split not only for 32 users, but for 64, 128, or even 256 users. And that's all very, very important for building bigger and bigger and faster GPON networks. The other really big advantage of the 10 GPON systems is they use slightly different wavelengths than the 1 gig GPON systems. What that means is you can take a system that's been operating, even for years, as a 1 gig GPON system, and you can add a 10 gig system on top. The wavelengths are different, and the 10 gig system can operate independently, simultaneously, over exactly the same cable plant. That means, for example, that if you had a large city with lots of business customers, you could run subscribers, individual subscribers who want their Netflix or Apple TV or Roku over the 1 gig system, which is plenty adequate for them, but overlay the system with a 10 gig system for business customers who might be downloading large graphic files for their movies. FTTH PONs have their own jargon, of course. We defined an optical line terminal, or an OLT, in the central office or head end, and the ONT, the optical network terminal, at the subscriber end. Basically, almost everyone agrees that the terminology from the head end or central office to the splitter is the feeder network. The splitter is in a fiber distribution hub, FDH. From there is more distribution cable to additional splitters, and then a drop cable to the home. So we have feeder to splitter, distribution to cascaded splitters, and drop cables to the home. And that's the nomenclature that's pretty much accepted for PON networks. PON wavelengths have also been standardized, and we'll use the GPON and BPON versions to show you what's typical. Each fiber is used bidirectionally, remember? The splitter allows us to split and combine signals so that we go bidirectional on a single fiber, standard G.652 single mode fiber. Downstream signals are sent at 1490 nanometers and upstream at 1310 nanometers. Early BPON systems were installed before Internet Protocol TV was widely available, so they used analog video just like a cable TV system. And they tended to use 1550 nanometers downstream. Because it was AM video and because it was going through a splitter, in some cases these early systems at 1550 required that the network have fiber amplifiers to get the signal level high enough to be usable with the splitters. Besides BPON, GPON, and EPON, there's RFOG, RF over glass. That's cable TV's fiber to the home solution. It works on the same cable plant architecture with splitters as a PON does, but it's basically a version of the hybrid fiber coax system used with cable modem service. It allows cable TV companies to operate over the same passive optical network as a GPON or BPON system. Passive optical networks use splitters. Splitters are passive optical branching devices, and they are bidirectional. So you can send the signal through one way and it splits it out to a number of users, and then you can send signals back through from the other direction, from any of those users, and it will combine them onto the same fiber that was the input. So it's I/O, input, output on all ports. They typically come in binary combinations, 1 to 2, 1 by 4, 1 by 8, 1 by 16, 1 by 32 configurations. Splitters can be cascaded for the desired ratio. So you can cascade a 1 by 2 and a 1 by 4 to get a 1 by 8, a 1 by 2 and a 1 by 8 to get a 1 by 16, and so forth. The loss of the splitter is 3 dB per 2 times split, plus some loss for the inefficiency of the splitter itself. Here's a table that gives you basically what the power ratios are for a splitter. So a 1 by 2 splitter has a 3 dB ideal loss. That's 50% in dB. It typically has an excess loss maximum of about 1 dB, so it actually has about 4 dB of loss. If you go all the way up to a 1 by 32 splitter, the ideal loss would be 15 dB, but the excess loss is about 4 dB, so you have a total of about 19 dB of loss. Many PON networks cascade splitters to design more efficient networks to connect subscribers. When you cascade splitters, you have two issues. You have to figure out what the split ratio is, and then you have to figure out what the loss is for the total loss to be included in the loss budget for your cable plant when you design the network. So here are some examples of cascading splitters to get up to a 32 split. And then we use the data in the previous table to calculate the loss. And you can see that the loss doesn't change that much to get to the 32 split. So cascading splitters is actually a very efficient way of designing networks. Passive optical networks are different in rural situations where the distances are long and the subscribers are less dense. Some designers have proposed not using splitters, but using taps. Splitters are special versions of passive fiber optic components that instead of dividing the signal into, say, two equal amounts, will divide the signal into a large and a small signal. So, for example, a 90-10 split or an 80-20 split and the like. And they have proposed using these taps instead of splitters for rural networks where you have a continuous fiber but tap part of the power off at each location. This can work in certain situations, but in the networks that we've tried to design using it, the excess loss in the splitters costs you a lot of distance. So it's really probably not going to be an ideal solution for most rural applications. What seems to be a much better solution for rural networks is a type of remote OLT. A typical OLT, like we showed you pictures early on, sits in a rack and can have dozens or hundreds of ports that can connect up thousands of users. But in a rural situation, you don't need that. So what the manufacturers of PON systems have come up with is remote OLTs. It only has one or two OLT ports. It's connected over Ethernet on fiber and can be daisy-chained. So basically, you can run from your head end with two fibers out to this little box that sits on typically a utility pole, and then drops fibers to splitters for those few subscribers that are in the area. Ideal applications for this are a small town, a cluster of farms, or we're actually seeing applications that utilities use it to also drop connections into a substation for utility grid management. FOA has YouTube lectures on fiber to the home architectures, this one on passive optical networks, another one on design, and another one on installation and testing. Besides these YouTube videos, the FOA has numerous pages on fiber to the home in the FOA Online Reference Guide, and a course on fiber to the home on FiberU, FOA's free online learning site. So there's lots more places you can go for resources to learn more about fiber to the home from the FOA. We're the Fiber Optic Association, the International Professional Association of Fiber Optics, and the worldwide known certifying body for fiber optic technicians. You can learn more about the FOA on our website, foa.org, where you can also have access to 1,000 pages of technical information in the FOA online guide. And you can go to FiberU, where we have more than 24 free online self-study programs to help you learn more about fiber optics.